Hello everybody, welcome back to Chapter 12 on Universal Gravitation. Our objectives for this video are to state and apply Newton's law of universal gravitation. And the content for this section is found in section 12.4, Newton's law of universal gravitation in your book. So the law of universal gravitation states that every object attracts every other object with a force that for any two objects is directly proportional to the mass of each object. The force decreases as the square of the distance as the centers of the mass of the objects increases. That is a mouthful, isn't it? Thankfully, we have an equation that sums it up a lot easier. Okay, so we're going to take a look at that equation. But first, before we look at the equation, we have to know about the universal gravitational constant, which is the capital letter G. Now, note, this is different than the lowercase letter g, which is the acceleration due to gravity, because they are different numbers. And so one is capitalized and one is lowercase. So the capital letter G, the universal gravitational constant, is the constant G in the equation for Newton's law of universal gravitation. It measures the strength of gravity. And notice, it is a very small number. G is equal to 6.67 times 10 to the negative 11th Newton times meter squared over a kilogram squared. 10 to the negative 11th means that this number has 11 zeros in front of it. So it is very, very small. Keep that in mind. We're going to come back to that. The equation, to sum up that mouthful of a definition, is F equals G times M1 times M2 over D squared. So what do all of those symbols mean? Well, F is force, which we've been using a lot. M1 is the mass of the first object. M2 is the mass of the second object, and D is the distance between them. So if we take a look at this equation, distance is on the bottom. So if we increase the distance, if we make that number larger, because we're dividing the top by that number, as it gets larger, the force gets smaller. So that means that as distance gets larger, the force between the objects gets smaller, which you realize this. You know that the further you get from the Earth, the less the gravitational force of the Earth on an object. Okay, so keep that in mind. Also, taking a look at the top, and that's inversely proportional and it's squared, so it has even more of an effect because it's squared. Now, on the top, we have the masses of the objects. We have M1 and M2. And for this part, that is directly proportional. So if we were to increase the mass, make one of these larger, that will increase the force. And if we were to decrease the mass, that would decrease the force. And you also know this intuitively, because you know that the force of gravity on the moon is less because the moon is smaller. It has less mass than the Earth, and that's why you weigh less on the moon. Okay, so you know that intuitively. So as an object moves farther from the Earth, the gravitational force of the Earth on an object decreases. We looked at the equation for that. We talked about that. So that's why this astronaut in space is not affected by the Earth's, is as affected by the Earth's gravitational pull because of the distance between them. As the distance increases, the force decreases. As the distance decreases, when the astronaut gets closer to the Earth, the force gets larger. Now, if the Earth were its present volume but more massive, we would weigh more. And we also talked about that with the equation, that the more mass, the more force. Okay? Now, gravitational forces are the weakest forces found in nature. And we know that because remember I said, remember about G being very small, the universal gravitational constant being a very small number? It's a really small number because gravity is really weak. Because of this, gravitational effects easily observed involve one or more large masses. That's why when we're talking about gravity, we're usually talking about planets. Because, in fact, there is a gravitational force between you and your computer right now. But the reason your computer does not fly at you and stick to you is because the mass of you and the mass of your computer is relatively small compared to that of the Earth. That's why if you were to drop your computer, it falls to the Earth. It does not fly at you. The gravitational forces between two massive spheres, like the Earth and the Sun, perhaps, is always an attraction. Number two, depends on how massive they are. The more mass, the more force. And depends inversely on the square of the distances between them. Remember we said the greater the distance, the less force. The smaller the distance, the more force there is. And that's a square, so it has even more effect. Now, let's take a look and use this equation. Suppose the gravitational force between two massive spheres is 10 newtons. If the distance between the spheres is cut in half, what is the force between the masses? Perhaps you could do this intuitively just by thinking about it, okay? But I want to use the equation. So here's our equation. F equals G times M1 times M2 over D squared. Now let's look at the numbers so we know what to plug in and what we're using. We are looking at just force and distance. So we're going to simplify this a little bit and we're going to make it into a ratio. Okay, so what I have done here is I have created a ratio between the first force and the second force. So F1 and F2 that I'm talking about in the problem. And because distance is an inverse relationship, D1 has to go on the bottom, just like for the equation where force is more on the top, distance is on the bottom. So for F2, D2 has to be on the top. They have to be flipped, okay, so that they're in inverse relationship and we are preserving that relationship with our ratio. So let's take a look at the numbers again. We have 10 newtons for the first force, and the distance is going to be cut in half for the second force. So what we do for our equation is we have F1, which is 10 newtons. We don't know F2. That's what we're after. But what we do know is that the distance for F2 is cut in half. And remember, because of the inverse relationship, it goes on the top. So we put that on the top, 1/2, and we square it. And on the bottom, we're just going to assume that our distance is 1. We're going to assign it the value of 1 and square it for this example. So when we square 1/2, we get 1/4, and when we square 1, we just get 1. Because remember, to square something, you multiply it by itself. So when we cross multiply, 10 times 1 is 10, and 1/4 times x is 1/4 x. So to get x by itself, we multiply both sides by 4, and we do that, we have x equals 40 newtons. So we have quadrupled the force by cutting the distance in half. Well, let's look at another scenario. Suppose the gravitational force between two massive balls is 10 newtons again. If the distance between the balls is doubled, what is the force between the masses? Well, intuitively, we know that if the distance increases, the force decreases. So if we get a different answer than that, we're in trouble. Okay, we're in trouble. So let's take a look at this. So again, we're going to use the same ratio as before. And remember the inverse relationship. We're going to look at the numbers again. We have our F1 is 10 newtons. And this time, the second distance is doubled. So when we plug that into our equation, we have 10 newtons for F1. We're going to assign X to F2. The second distance is doubled, so we're going to say that that is 2 squared. And the first distance, we're just going to assign the value of 1, so it is 1 squared. So when we square those numbers, we have 4 and 1. When we cross multiply, 10 times 1 is 10. 4 times x is 4x. Solve for x, and we get x is 2.5 newtons. And we expected the force to decrease. Now, last scenario. Suppose the gravitational force between two massive balls is 10 newtons. If the magnitude of each mass is doubled, what is the force between the masses? So this time we're not dealing with distance, we're dealing with mass. So we're going to go back to our equation, F equals G times M1 times M2 over D squared. And we're going to go back to the problem and see that we're dealing this time with mass and force. So this time our ratio is going to be F1 over F2 like before, but now it's the masses. The mass of the first object times the mass of the second object over the mass of the third object times the mass of the fourth object. We do not flip these this time because mass is a direct proportion, not an inverse, not indirect like the distance. It has a direct relationship. So we have 10 newtons and our masses are doubled. So here, F1 is 10 newtons. We're going to assign 1 as the value for the masses of each of those. We're going to have that over F2 is x because we don't know it. And the masses of the the third and fourth object are 2. The mass is doubled. So 2 times 2 because both of them doubled. So when we simplify that, we have 10n equals 1 over 10 and x and 4 here. So when we cross multiply, we get 40 newtons. Okay, and we know that if we increase the mass, we're going to increase the force. So our objectives today were to state and apply Newton's law of universal gravitation. And so we stated it, we looked at the equation, we applied the equation, and we talked about the concepts with that. So don't forget your 5 questions, and I will see you later with another video.